Hi everybody, Mr. Higgins here. I'm just going to run through a quick video to show you how to calculate the bond enthalpy of a reaction. So that's what we were doing today in class. So for anyone who wasn't in or anyone who's not sure and needs a little bit of help, please watch this and it'll hopefully help you. We are going to calculate the bond enthalpy for the complete combustion of propane. So complete combustion of propane. Now, hopefully you can see that it's not particularly good on the camera. Hang on, I'll just zoom it. I'll just bring it down a bit and see if it zooms. See if it can pick up a bit more focus. Well, hopefully it'll pick up in a minute. Right, so the first thing you need to do is for any reaction where you're working out the bond enthalpy, you need to write out a balanced symbol equation. So propane has the formula C3H8. And if I've got complete combustion, what it means is that I'm reacting it with oxygen, so plus O2. And as you should know, complete combustion of any hydrocarbon always has two products, carbon dioxide and water. So we've got CO2 plus H2O. Now the first thing is that we need to balance this. If it's not balanced, our equation's never going to work, and now therefore our results are going to be wrong. So I've got 3 carbons on the left hand side of the arrow. I'm just going to focus this again. Focus is a bit dodgy at the moment. I think that's the best I can do. So, 3 carbons on the left hand side of the arrow, and I've only got 1 at the moment on the right hand side. So I need 3 carbon dioxide molecules in order to balance out my propane. I've got 8 hydrogens on the left hand side, and I've only got 2 on the right hand side. So in order to balance out that propane, I need to have 4 of these water molecules, and now all I need to do is balance out the oxygens. So I've got 2 times 3 oxygens here, that's 6, and I've got 1 times 4 oxygens here, that's 4, so 6 and 4 is 10. An oxygen molecule over here which has 2 atoms in it, and therefore I need 5 of those molecules to balance out the oxygens. So that's it, we've now got our balanced equation. The next thing that's important is we need to know the structure of these molecules. So propane, we've already done. We've talked about that when we did crude oil, fractional distillation and alkanes. So the structure of propane looks like this. You have 3 carbons in a chain, and each carbon is bonded to hydrogen atoms until it's made 4 covalent bonds. That's the structure of propane. Oxygen, 1 oxygen molecule has 2 atoms with a double covalent bond in between them. So like that. Carbon dioxide, you have a central carbon atom and a double bond on either side to an oxygen atom. So that's what that looks like. And then a water molecule, hopefully you'll be aware of already. You have a central oxygen atom bonded covalently to 2 hydrogen atoms separately. Now please bear in mind that this molecule, we have 5 of them, this molecule we have 3 of them, and this molecule we have 4 of them. Okay, so the next step is we need to find out our bond enthalpies for each individual bond. So this is the sheet that I've given to you on the, either in class, if you were in class it should be stuck in your book, or if you're at home this sheet is given to you on the worksheet. So what I need to do is I need to figure out which bonds I've got. Alright, so I need to work out all the bonds in this molecule and all the bonds in 5 of these molecules, and then the bonds in 3 of these molecules and 4 of these molecules. Now in order to work out your overall enthalpy change, the enthalpy change equals the sum, so we use the symbol sigma, so the sum of the reactants take away the sum of the products. In other words, I'm going to work out all the bonds in my reactants, so the left hand side of the arrow, and I'm going to take away all the bonds on the right hand side of the arrow, my products. So let's work that out then. As we can see in here, in propane, I've got 2 carbon to carbon single bonds, and on your bond enthalpy sheet, a carbon to carbon single bond has an enthalpy of 348. So I need to do 2 times 348. Okay? Plus, I've also got, I'll try and use a different colour for each one. I've got 1, 2, 3, 4, 5, 6, 7, 8 CH single bonds. So I've got to do plus 8 times, and a CH single bond has a bond enthalpy of 413. Plus, I've also got oxygen double bond. But bear in mind, I've got 5 of these molecules from balancing our equation, so I've got this times 5. So plus 5 times, and if you look on your bond enthalpy sheet, just show you where this one is, an O2 molecule says 495. I don't really know why it hasn't just put oxygen double bond oxygen there, but it just says O2, but that is the one we're looking for. So 5 times 495. Now, because we're doing the sum of the reactants, I want to put big brackets around all of that. Okay, and I'm going to take away my products. In order to get my products, here I've got 2 carbon-oxygen double bonds, but remember I've got 3 of these molecules, so I've got times 2 by 3, so I've got 6 carbon-oxygen double bonds. So 6 times your carbon-oxygen double bond, which is 799, plus I've now got 2 O to H single bonds, but again there are 4 of these molecules, so 2 times 4 is 8 of those, so I've got 8 times, and your oxygen hydrogen is 463 kilojoules per mole. Again, I want the sum of all those products, so I'm going to put big brackets around that whole thing. Now, the easiest way for you to do that is take out your calculator and put in that big long calculation very carefully, and you will come out with the correct answer. But if you're not particularly comfortable doing that, you can work out each of these small brackets individually and then do the total, which is what I'm going to do for you just to make sure we're happy. So 2 times 348 equals 696, plus 8 times 413 is 3,304, plus 5 times 495, I should say, not 49, sorry about that. So 5 times 495 is 2,475. So that's the sum of my reactants. Take away my products. 6 times 799 is 4,794, plus 8 times 463 is 3,704. So now if I do this calculation, take away this calculation, so that overall this bracket equals 6,475, take away this bracket, which equals 8,498. My overall answer should be negative 2,023 kilojoules per mole. Okay, now what is really important here is that sign there. Okay, a negative sign for bond enthalpy means exothermic. It means that that amount of energy is being released by this reaction. Now we should hopefully be able to work that out straight away because it's a combustion reaction. Combustion reactions are always exothermic, but this proves it because we've got a negative value. If that value there is positive, then the reaction is endothermic. Thanks guys, I hope that was helpful. Cheers, bye bye.